While we're waiting, how are you, Fan? What time is it for you? I probably mispronounced your name.
I'll ping him in Discord. Maybe his audio is not right.
All right. Who do we have on so far? Oh, hi, James.
Hi, how are you doing, Bernard?
Good. How are you? How are things going?
Oh, I can't complain. It's all good.
That's good.
Yeah.
Doing things. Almost there. Almost there. It's all good.
Cool.
All right. We're just waiting for Evgeny and Dmitry, I think. Then we can kick it off. You got to rework that one link on the registration link, apparently.
I will comment on that. Okay. It's super annoying.
Okay.
I don't know. Maybe we just have to do it in Discord next time.
Well, we should. The live platform seems pretty cool. Haven't tried it, so.
Which one?
The live platform they're using. I mean, I've attended a few in Discord, those live events.
Mm-hmm.
They seem pretty good. All right. That's the all right. Okay. All right. At least from the Fluence side, where we seem fairly complete. So everybody, welcome for another edition of the biweekly Fluence community call. Today, the agenda is that we have an update from the core team, which actually just came back from a week-long summit. And then we're going to have a demo from around self-ID, ceramic, and Fluence from Fan, who won the bounty in the hackathon. Question and answers, open discussions, and then we're going to get a super cool lecture from Pavel about the Java SDK Fluence for JS developers. I think I'll hand it over to Dmitry now.
Hello. So just a few quick updates. I counted 4 updates to share today. First, I'm waiting for Fan to join. I think it makes sense for Fan to join.
He's resetting his Zoom because he didn't hear us.
Okay. So first of all, we released the new version of Aqua with the new version of Aqua VM and rolled it out to the network and to the Fluence-JS implementation of the Fluence Peer. And it's like it contains small improvements from the usage point of view, but it fixes some really obscure bugs and issues that many hackers were facing. It scoped streams. So previously, when you use the streams inside for loops in your Aqua, you could have met some really strange behavior of Aqua, that it kept the state of the stream between iterations. And now the streams are isolated. And it means that you can safely use streams to build data within the functions, which then will be called inside the for loop. And that's just nice and more intuitive. That's a breaking change. So if you want to use it, if you want to have a more stable Aqua, please update to Aqua 0.5. FLD's run is not supported, at least for now. So you have Aqua run instead, which compiles and runs Aqua in a single like CLI command. Be sure that you updated Fluence.js and the node Docker image as well. So the second update is that after we rolled out the asynchronous virtual machine inside Fluence Peers, we were looking for the best ways to use it. Now we have a very widely used pattern enabled in Aqua and in Fluence. It's race conditions, for example, the race with the timer, which leads to a timeout pattern. So now you can isolate a block of code in Aqua, wait for some time for it to be executed. And if it doesn't, then you'll have an error and can wrap it with some failure logic. So that's also pretty nice. And we had a lot of requests about it. And two more updates, which are not in the dev channel, not on the list of updates, but will be hopefully soon. The first is that there is a very important piece of this Fluence security model called Trust Graph. Now we have Trust Graph live. The service is already bundled within the Fluence node, and you can try it out. You can utilize it. You can build your logic at top of it, and that's pretty good and pretty important. It will have a lot of consequences. I think that we will have a dedicated Trust Graph related meeting in the following weeks to highlight the usages. But just to give a hint, Trust Graph is designed to solve two big problems. The first one is priorities for resources, for shared resources in the open network. So you can prioritize some peers or some groups of peers or some peer hierarchies to be sure that they will have the resources that you want to allocate to them using Trust Graph. And the second problem is labeling or attributing peers with cryptographic signatures, cryptographic relations. So this could be used for permission management, which is shared across different parts and protocols and applications on the Fluence network. So we have it live. We have some examples in the code and working on the proper announcement and documentation to provide in the dev channel. And the last is that we spent the whole week on the Fluence engineering offsite event, which was pretty intense, and hopefully it will be materialized in form of roadmaps for the Fluence components and much more fresh, wonderful content from the core Fluence team. So this is also just an announcement for what's going on and what we will see soon. I'm done with the updates. There were 4.
It was awesome. Anybody have any questions? As a bonus for those on the call, I haven't updated our documentation from FLDIS to Aqua yet, so bear with me for a day or two. If you run into problems, ping me on Discord. We'll show you how to use Aqua Run instead of FLDIS. Okay. Next up is Fan. He won the ceramic hackathon around self-ID, and he's gonna tell us all about his project. Fan, you're up.
Yes, I can hear you. Can you hear me?
Yes.
Okay. So let me show my documentation first. Can you see my screen?
No.
Not yet.
Sorry. My setup is not okay. Can you see my screen?
Yes.
Yes.
Yes. Looking good.
Okay. This is a documentation. The user first start the authentication in the web using the ceramic self ID, and after the successful authentication, a DID will be returned. And using this DID to request the greeting service through the all service. The all service is in the middle. It maintains a hash map. If the DID is containing a hash map, the user has a permission to access a greeting service. If the DID is not contained in the hash map, the request will be rejected. So the logic is very simple. Let me show you the example. This is a main page. And if we click the greeting button, because we are not authenticated, it is rejected.
And, probably you want to show something else. We still see the README page. The window with README.
Yeah, it doesn't show your browser.
Okay. The user first start the authentication in the web using the ceramic self ID. And after a successful authentication, the DID is returned. And we request the greeting service using this DID. The all service is in the middle. If the DID is contained in a hash map, the all service maintain a hash map. If the DID is contained in a hash map, the permission can be granted to access a greeting service. If the DID is not contained in the hash map, the request will be rejected. So it is a very simple method to authenticate the service, the greeting service. So anybody has any question?
Yeah, didn't you have a demo on how to run it, like in the browser?
Yeah, I have. See, this is the main page. Because we are not authenticated, if we click the greeting button,
No, we cannot see the browser. We cannot see a browser window.
what,
Like you need to share the browser window, the screen.
okay.
Maybe just stop sharing and share again. Just pick another window and it should work.
Okay, let me try. Can you see the browser?
Yes.
Yeah, it is visible.
Okay. First, if we don't authenticate, click the greeting button. Because we don't have authenticated, will be rejected. It is showed you are not authenticated. And then go to the permission tab. Click the self ID authenticate. And now we are authenticated. Go to the service tab. Click greeting. It shows a hi message with the DID. If we go to the permission tab, remove the DID and return to the service. It shows not authentic. The key is to add the DID to the permission map in the auth service. Any doubt?
Yeah, so this is pretty cool. So why is this a big deal? I mean, what's the big deal about self IDs and DIDs, particularly self ID from Ceramic, which you used? What's the benefit of using that for authentication, and why is it important in decentralized systems?
The self ID is means you can have your own data. We don't need to store the data with a centralized storage service. We stored it on the decentralized network. I think that's a benefit of using the DID. The DID is a decentralized identity. Nobody can control it.
Right. But I mean, one of the advantages of DID is also that it's sort of one key set for different, basically universal, right? Because I mean, self ID itself integrates with a whole bunch of different blockchain wallets as well, right? So you can use the wallet.
Yes.
Okay. So that basically the entire key management now can be reduced to a wallet holding it, and then you can control in a decentralized manner any
Yes.
service or transaction submission to any on or off-chain blockchain, basically, right?
Right.
Okay, so that's pretty powerful, isn't it?
Sure.
That's why I think what you did is really cool, because it really pushes that authentication authorization level into the DID space. Okay, anybody else have any questions for fun?
I'm just curious about the lessons that you have learned while working with Fluence, and if there's any piece of code that you have written in Aqua or with Murygin, and if you can share it and say something about it, it would be super interesting.
Yeah. The Aqua is quite simple. The syntax is very simple and very easy to understand. I think have a programming background can understand it very quickly. And the service, the Murygin service, I think it's also a different kind of Docker service, I think, because I used the Docker before. It is like a service. After I tried the Fluence, the Murygin service, it is quite similar with the Docker service. I get a feeling it's a decentralized Docker service, Kubernetes, decentralized Kubernetes. And I think it's very powerful in the future.
Cool, thank you.
Yeah.
Anybody else? All right, cool. Well, thanks, Fun. Well done. Thank you very much. It was awesome. Thanks for the presentation, taking the time. And I think next on the agenda we have question and answers. Any questions? Possibly any answers? Anybody have questions about anything related to Fluence, Aqua, the summit?
Fun, you're still sharing the screen.
Yeah, you're still sharing.
Okay. Let me close it.
All right. Silent crowd today, silent crowd. Well, in that case, I'll hand it over to Pavel, who's going to tell us everything you ever wanted to know and needed to know about Java, the JavaScript SDK from Fluence. Pavel, all yours. We can't hear you. You're on mute.
Oh, I'm so nervous. This is my first talk on the community call. I forgot to unmute myself. Hi, Bernard. Thank you. So let me share the screen. Is it sharing?
Yep.
Yep.
Great. And by the way, I think the term JavaScript SDK is a little bit misleading. So we've renamed it everywhere to Fluence-JS. And I hope this is my opportunity to tell me exactly why we did this and what should actually constitute an SDK for a front-end developer who wants to develop an application for Fluence. And first, let's start with a little bit of description of the Fluence, maybe for people who are just learning Fluence for the first time. Maybe they are viewing this video on the YouTube. So basically, Fluence is a peer-to-peer application platform, and Fluence provides a development stack with a lot of tools to help developers building peer-to-peer applications and hosting them onto the network. And by the way, the network is live. You can develop and deploy services there and deploy applications. For more info, visit, I guess, our previous calls about Fluence, mainly the introductory one. I will focus more on the JavaScript side of our stack. So Fluence as a network consists of peers, obviously. And every peer runs an Aqua virtual machine. This is basically a driving force for the network. Aqua virtual machines process particles, and particles are programmable message packages that are used to share data between peers and communicate between peers. So I hope my cursor is visible. This is like a tiny schematical representation of the network. Every square is a peer, and it runs WebAssembly Aqua VM. And by the way, peers are roughly divided into two classes. The Rust Fluence nodes, which are kind of backend nodes running in the network. And we also have implementation for clients like browsers, maybe mobile devices running JavaScript and stuff like that. We call them clients. And actually, this is what we are interested here. Clients connect to the network via relays. We'll talk about that later. And they're implemented in TypeScript. Just a little bit about the communication. So our message is called particle. It contains both code and data. And the code actually encodes how the particle should travel through the network and what should it call from different peers. Particles, well, we can say for the sake of this demo that particles can be programmed with Aqua programming language, and here on this scheme, these green dots are particles traveling from peer to peer, sending some important messages, let's say like that. So about TypeScript peer implementation. It has everything needed to participate in Fluence protocol. So as I've already said, it runs Aqua virtual machine. It has the peer ID to identify itself in the network. It has the connectivity with JS implementation of peer-to-peer. It also has all set of built-ins required by the Fluence protocol, so it can be viewed as a first-class citizen in the Fluent network. Unlike the Rust implementation, which is like our backend or distributed cloud main computing power, JavaScript or TypeScript client has some differences. First of all, as I've already said, due to the limitations of browsers, it has to connect to the network via relay. Relay could be any node in the network. And all the particles are sent to the relay, and then only after that they are routed into the network. Also, TypeScript implementation does not allow to host Murygin services, basically services that are composed of WASM modules yet, because we're actually working on that. Also, contrary to the Rust node, you can directly implement services in plain TypeScript or JavaScript. And this is very handy for front-end applications where you can provide some code for the callbacks or services that are running in browser very quickly without need to write a lot of Rust code and compile it to WASM and stuff like that. It is very user-friendly. Also, TypeScript implementation allows you to actually initiate the particle processing. So you can send a particle, and that provides a great opportunity for user interfaces to provide the entry point to the network and the ability to communicate with the network. Also, I will talk about Aqua, and Aqua provides first-class compilation target for the TypeScript peer. And this with the combination of the ability to initiate particle allows you to actually program user-facing applications with Aqua and the TypeScript implementation of the peer. Before we proceed, I have to show you a little bit of Aqua and how it is translated to TypeScript. For a more in-depth introduction and more in-depth info about Aqua, I guess you should visit our previous community call, and you can always refer to the documentation as well. Here we will be focused mostly on the TypeScript part. So first of all, services. You can define the service in Aqua like this. And for the Aqua definition, the compiler provides you with two entities. First of all, it's the description of the interface. Basically, it is an object with keys mapped to the corresponding functions in the service. And it also provides a function which is called register and the name of service. If you call this function, you will be able to register the service, provide the implementation for the service. And when someone calls the service from Aqua, your implementation will be get called. Second is the function definition in Aqua. Oh, unfortunately, my syntax highlighting doesn't work here. But anyway, here are two examples of functions in Aqua. One which has a return value and an argument, and another has nothing. And for the functions, the Aqua compiler generates you basically a function in TypeScript. Everything is type checked, and you have support from IntelliSense, for example, if you're using VS Code. For functions which return values, they correspond to promises with return value, actually, and non-return value functions, they do not return any value. And here's little, there is a little catch. Please note that when you make a function do not return anything, the function, the corresponding TypeScript function will succeed just after the particle is sent to the network. We will get to that later about particles. So it won't catch any runtime errors during the execution of the Aqua script and the Aqua code. If you really want to handle errors, you have to provide the return value. Just any kind of acknowledge is okay. And if the function has the return value, then it will catch all the errors that happen during the execution, and the promise will fail with a user-friendly error message. So you have to keep in mind it when you are designing your functions. A little bit about types. The conversion between Aqua types and TypeScript types are pretty much straightforward. The only interesting part here are arrow types. So for every arrow type, the Aqua compiler will create a callback in the form of a function. So for example, here we have an arrow of a string and integer, and it will create us, the Aqua will create us a TypeScript definition of a function with actually arguments of exactly type string and a number. So Fluence provides, as I've already said in the beginning, we provide the Fluence-JS package, which provides some useful stuff for front-end development. And first of all, it is actually the implementation of the Fluence Peer itself. The Fluence Peer class has a public interface, which you are free to call, and we also have internal interface. I will go to it later. Basically, it is needed to interop with the Aqua compiler definitions. Also, we provide a default peer. Basically, every time you call the function like this, you're creating a particle and then executing it from the default peer defined in the Fluence.js package. This is, I think this is enough for the vast majority of use cases, and you do not have to worry about the exact peer where the execution is happening. But you can always get this peer and get an instance of the Fluence peer, and you can also create the peer manually, and you will only need it for advanced cases where you actually want to run many peers inside the browser. And I won't be covering this during this talk. You can feel free to refer to the documentation. We have this section describing usage of several peers. So just quickly to finish with the Fluence package overview, we provide the facade, which wraps around this default peer and provides a set of common operations with the peer. And there is also a compiler support, which is not used publicly, but it is very useful and is needed for the Aqua compiler to do its magic. So this is the interface for Fluence Facade. It is very simple. Basically, it allows you to start peer, to stop it, and to get its status. We are working on that status, and it will be extended very soon. And speaking of the Fluence Peer public API, it is very similar to the Facade one. Basically, it almost corresponds one-to-one to the Facade API, but actually the Facade API calls these functions from the default implementation of peer under the hood. There's also one neat function which can help you to check if any JavaScript object is an instance of Fluence Peer, and it is actually used in the Aqua compiler support as well. So let me tell a little bit more about the Fluence Peer internally. So under the hood, the Fluence Peer, as I've already said, it has an Aqua virtual machine. It also uses libp2p for the connectivity with the network. And it provides something like a service registry where actually all the service registrations are stored and from where they get called. So everything is connected using queues, or I'd rather say RxJS streams. If you want me to tell more about it, feel free to ask any questions. And regarding the internal API, the one which is used by the Aqua compiler under the hood. So first of all, the initiate particle, this is the magic. Oh, and by the way, yeah, I guess it will be, my demo will highlight it for me. So initiate particle is where the particle initiation starts and what makes it possible to call all the functions made by the Aqua compiler. And there is a service registration object, let's call it like that. There are, under the hood, we divide services like all the common ones and the one specific for particles, but they are more or less the same. Just some magic to help the compiler pick the correct service when the particle comes to the peer. There is also a handler for callbacks, and with all of that, the Aqua compiler can generate its functions. So let's see how it works under a hood. For example, for a function named say hello, the compiler generates, first of all, it generates a set of overloads corresponding to different type of arguments passed to the function. As you can see, you can pass the peer as the first argument, and that way you can execute the function on a different peer. Then goes the actual implementation, and under the hood, this call function is called, and this is where the glue code resides, the glue code between Aqua compiler, well, this definition here, and the actual conversion to particle and particle format. This is where it's done. Similar to that, for service definitions, there are several entities that are generated. First of all, it's the interface. It's very handy to import it in the application code. And then there are several overloads. The same way, you can always pass Fluence Peer as the first argument. And then there is the actual implementation, which under the hood calls the register service function. And that's roughly the same as the call function, but for service registrations. So now let's talk a little bit more about how you can actually build something with Fluence.js. And that's where I should talk about the SDK. So basically, building blocks for a front-end application are many. First of all, it's the Aqua code. You will need it to write peer-to-peer communication logic. Also, you need the compiler CLI. Well, you need it to compile Aqua code into TypeScript. Of course, you need the Fluence package with the which provides everything I've been talking about before. Of course, you will need the JavaScript environment. We have both examples for Node.js and browser. Our SDK is tested, and it is working in all modern browsers. So you are free to choose the environment for you. And of course, you will need to write your application code, and there are no restrictions for you there. You can use any framework. You can use it without framework. So I would say that the SDK for JavaScript in Fluence consists of at least two things. That's the Aqua compiler, and that's the Fluence.js package itself. And I'm not sure, but we can probably consider the Aqua code somewhere close to this SDK as well. So the whole SDK is a set of tools, but Fluence.js is actually the package which provides you the implementation for the part of this tool set. So in order to write the application, you have to install the dependencies. One interesting dependency I want to talk about is Fluence network environment. This is a package where you can find lists of the nodes of known Fluence network. For example, our Krasnodar network, which is kind of like our most user and front-facing network. All the examples are pointing to that, so you can find it in the Fluence network environment package. Of course, you will need the compiler, and you can install it as a development dependency. You don't need this code in production, but it is needed to compile Aqua at the compile time. And we highly recommend automating the compilation, and we use Chokidar in our examples. So we will have Chokidar in this demo as well. So after you install the Aqua compiler, it can be called with an npx, but it is much more convenient to have separate scripts like this one for to just call the Aqua compiler, and we use Chokidar to watch the directory for the changes in Aqua files and to run the compilation automatically. And after you define such scripts, you can call them via npm. Okay, let's have an example. So this is an Aqua code for our application. Here on the first line, we are importing built-in functions. We will need them. This is the service definition. It will be the service will be run in the browser, and it has a single function which has an argument of a peer where the call came from, and it returns a string. And here is the function which does very simple thing. It goes to the target peer through the target peer's relay and calls the service we defined above and returns the result back. So if you compile this code, you will get the TypeScript file, and let's see how you can use it in the application. So first of all, I want to say that this is the demo with the React, but it can be done without React, as I've already said, with other front-end framework, or even without it. So I will focus on the Fluence part. So first of all, we import Fluence, the facade I've been talking about earlier. This is the Krasnodar network I've been talking about. We import that from the known packages. And here is where we import in functions generated by the Aqua compiler. So this is how we start the Fluence node. I mean, here's how we start the default peer, this peer which is running inside our current browser. And we are registering a handler for the hello of the hello world service. So we are just setting some hello message somewhere in the input and returning back a welcome message. And this is actually, this is the incorrect line. I wanted to highlight this one. This is how you call the function. You call Aqua compile functions just like any normal asynchronous TypeScript function. And we are calling say hello, providing it with some peer ID and its relay. We get them from the inputs, and I will show it to you in the demo. So demo time. I've already opened the project, and here is our code. Everything is already installed. I just wanted to save you time. The only thing I would like to do is to compile Aqua. to show that it is compiled. Here is the generated output from the Aqua compiler. This is the interface for our service. Overrides for the service registration, and here is the implementation for the say hello function. Actually, this script, it is called AIR, which stands for Aqua Intermediate Representation, and it is the part of the particle. And this is the code I've been talking about in the beginning. This is actually our application. Let's just start it. Okay, so we have two browsers, each running our application. Let's connect to different relays. And we want to say hello from this peer to this one. So we copy the corresponding peer IDs and relays. And here it works. So getting back to the demo, actually, this was, I guess, the introduction to the Fluence-JS. Feel free to refer to our documentation. There is no link to this presentation, but I think I will upload it somewhere, and we will attach the link under the YouTube description, because I think this recording will be on the YouTube, so you'll be able to play with this presentation as well. So thank you for your attention. Any questions?
All right, thanks, Pavel. Questions, anybody? All right, I got a question for you, just in case. I saved this up for the last couple of days. And the Rust nodes have a lot of built-in functionality, which we can easily access from Aqua. And I was wondering if those capabilities are available from the JS-based nodes as well.
Well, there are, I guess, several types of built-ins, some of which correspond to the Murygin. That's about creating services, uploading modules and stuff like that. Obviously, JS implementation doesn't support that, but all the built-ins like identity or timeout and stuff like that, they are fully supported, so you can use them.
Very cool. So most of the peer stuff and some of those are all available, right?
Yes, of course.
Okay, cool. Yeah, just double checking. I think that's an important point. I think of when we look at it, that there's an equality or an indifference for Aqua, what node you're hitting on, right?
Yes, of course, it is different, and you can see this difference.
No, but what I mean is for Aqua, it does make a difference. So if I'm, for example, if I wanted to use peer timeout or use peer timestamp,
you can.
I don't need to know what type of node I have in my neighborhood. I just use
that's
Aqua,
right.
And it's okay. Cool, very cool. Anybody else have any questions? Well, then. Thank you, Dmitry. Thank you, Fawn. Thank you, Pavel. It's awesome. And for those of you celebrating Thanksgiving, happy Thanksgiving. For the rest of you, too bad. And we'll see you in 2 weeks, right, Anna?
Yes.
All right, cool. Thanks, everybody. Have a great week. Have a great weekend. See you in a couple of weeks. Bye-bye.
Bye.